Equilibrium occurs when you have rates of reactions equal to each other in both the forward and reverse direction. And yet many chemical reactions start out of equilibrium by definition. To represent this non-equilibrium state, we have what's known as the reaction quotient, which is a snapshot of where the reaction conditions are with respect to equilibrium. The reaction quotient Q is calculated using the concentrations of both reactants and products at any given instant during the course of the reaction. And we can use the reaction quotient to predict which way a reaction will go to get to equilibrium. If you always write the reaction quotient and equilibrium constants in alphabetical order, that is, you compare the the equilibrium constant K to the reaction quotient Q, then what you'll find is that when you have K and Q, the greater than or less than arrow will point in the direction the reaction should move. So when K is less than Q, there's too much product, and therefore the reaction will move towards reactants, as seen by the reaction arrow, which we would draw this way. Whoops, sorry about that. And if K is greater than Q, then the reaction is going to move towards products. So how do we calculate the reaction quotient? Well, it is quite literally a plug and chug math problem. You take your reactant and product concentrations or pressures at any given instant, plug them into the equilibrium expression, and you then can compare K and Q. So in the first two cases here, I'm just going to skip over that, but we could see here when we put in, for example, 0.7 for N2O4 and 0.3, and we square that because it's squared in the equilibrium, then what we get is 0.129. So 0.129, and I've run out of space here, so we'll say K is 0.212, and that's greater than 0.129. We would predict that this reaction would move towards products to get to equilibrium. We can do the same thing for experiments 4 and 5 here, just plugging and chugging into this equilibrium expression, and I'll let you guys actually do that, but you should get 0.5 when you do experiment 4 and 3.2 when you do experiment 5, and when you compare those Q values to K, you can see they move towards reactants. So how do we find equilibrium when we're given a set of initial conditions? Well, we use something known as an ICE table. Now, an ICE table is not a table made by this man. Rather, it is a table in which you have an initial change in equilibrium column and your reactants and how they progress through these changes in these nice columns here. And so what we do is we always track through things we know are our initial conditions, and then we can predict changes by using the variable x and the stoichiometric relationships to indicate changes in one direction or another, and then actually calculate what we would expect to have at equilibrium in terms of pressures and concentrations. So, for example, here I've got a problem involving hydrogen and iodine producing hydrogen iodide, and I have a couple of initial conditions, but I also have a final condition, which is not typical in these problems. Most of these problems, you won't actually know anything about what the concentration is at equilibrium. But to start with, we'll do this because it's a little easier to see things. And so I set up my ICE table having this initial hydrogen and iodine concentration and no HI at the initial time of the reaction. And if something's not given to you, you just go ahead and assume it's 0, because if you were expected to know it, it would have been stipulated at some point during the problem. So what do we see? We have two initial reactants, no product, and we know by the end of the reaction, or when it reaches equilibrium, we've increased the product concentration to 1.87 times 10 to the minus third, which means the HI concentration went up by that. Well, because the reaction is actually, if we were to write it here, it would be H2 plus I2 goes to 2HI. So the concentration of HI increases twice as much for HI as it would for I minus or H2. And so because of that stoichiometry, we can see we're going to decrease the reactant side because it's going to make product. It's going away. And what we see is we've got the HI increasing by twice of 9.35, and that again comes from the stoichiometry. And so at equilibrium, it's literally adding the initial and change columns here. So you can imagine taking these two values, adding them together, and in this case you get 6.5 times 10 to the minus fifth. You do the same thing for the I column, and we were already given the HI initially. But what if we don't know what the equilibrium pressure is or the equilibrium concentration is, and we're just given initial conditions? How does that change things? Well, it changes in our ICE table in that we don't have values to use for the change. We actually have to use the variable x. And so the variable x, again, is based off of the stoichiometry in the balanced equation. So here we have reactant, product. Well, there is no product, so we know the product side has to increase, so that's why we get this positive 2x here. But we also know the reactants are going to decrease because one side has to go up, the other side has to go down, so we have a negative change, and we say it's minus x because the stoichiometry in the problem is minus x corresponds to minus 1 hydrogen, minus x corresponds to 1 iodine, and the product of plus 2x means that you get twice as much HI. So at equilibrium, what we have is concentrations which reflect the change from initial conditions. Well, once we have the E in the ICE table, what we can do is take these values and put them into our equilibrium expression. So the 2x we saw from the previous slide, for the HI concentration that goes there, it's squared because we have the 2 in the balanced chemical equation. We have our two final reactant concentrations, and we know that the equilibrium constant, which was given to us, is equal to 50.5. So we can go in and actually solve for what the value of x is. And when we do that, because this produces a quadratic, we get two roots. One of them is meaningful and one of them is meaningless. So the two roots mathematically are 2.3 and 0.935. However, when we apply these values to x, we have to remember that we're dealing with a real-world situation, and that if I take 2.32 and plug it into my 1 minus x or my 2 minus x, I'm going to get a negative concentration, and that makes no physical sense. It's impossible to have a negative concentration. So only the root 0.935 works. And so you always have to go back and check to see if what your values of x or your answers to the quadratic are actually make sense. And one of them should. If you've done everything right, you should have one answer that makes sense and one that's completely bogus. If you have two answers that don't make sense, then something's gone wrong. You've forgotten a sign or you've forgotten to square something. So keep that in mind.